Hello guys, I am Dr. Devendra Mishra, working as Assistant Professor in Chemistry at Bidla Institute of Applied Sciences, right? Also running this Tetrahedron Chemistry Classes channel, and here are the links available to. Hello friends, welcome back to the Tetrahedron Chemistry Classes. So guys, in my third lecture of organometallic compounds, today I am going to take a very important topic, right? That is metal-metal bond in the polynuclear organometallic compounds. See, when I say the polynuclear, that means it will have more than one nucleus, and these nucleus actually would be the metals, transition metals. They would be either of the same kinds, right, or the different kinds, and their numbers could be 2, 3, 4, 5, 6, anything, right? But I'll not go beyond four metals, because when you have the clusters actually say 6, 4, 5, 6 metals, then actually the concept becomes little tedious, and for this we will see the Wade-Mingo rule later on, right? But today I am going to explain this concept of how to find the metal-metal bond in the organometallic compounds. Okay, so for this you need to understand the nature of the ligand. You know, the ligands can act actually in two ways. Actually, if you have your ligand, for example, like I am writing ligand here, then your ligand may be terminal, okay, and it may form a bridge. And when this happens actually, then see, in case of the neutral ligands there is no problem. If the ligand is the neutral, then it doesn't matter whether the ligand is the neutral or the bridge ligand, it will always contribute the same number of the electrons, right, towards the bonding. But if your say a ligand is not neutral, say for example if you have the Cl negative, right, if you have the Cl negative, then this Cl negative, if it is actually terminal, so in case of the terminal, say I'm writing T, it will contribute only one electron, that is equal to its formal charge which is present on it, okay. But when this Cl negative actually would act as your say bridging ligand, then in that case it will actually contribute more than one, and say it's 3, okay. So in this way you have to understand the role of the ligand. So however I will explain these things in each and every type of the example. So but you need to know actually, right? So how actually this is connected, right? So when it is forming only one ligand, it is this will give you actually only this will give or contribute 3 electrons, when actually it will form only one bridge. And one bridge means, that mean, if you can write this mu2Cl. Mu2Cl means it is connecting the two metals actually. So in that case it will contribute 3 electrons, okay. But if it is connecting say more than two metals, right? Say for example how I can write, say for example I am having mu4Cl, okay, mu4Cl. So in that case, if you see the electronic configuration, right? So 1, 2, 3, 4, 5, 6, 7. This is the valential electronic configuration of the Cl negative. Okay. So how many electrons it can donate actually? See, remember one thing: whatever the donation of the electrons would be done by the ligand, right? It will actually the ligand will do these things only after forming one covalent bond. Okay, that means first it will complete its octet, right? And then after that it will actually donate electrons. So for example, in that case, if it is terminal, I am saying it is terminal, okay, so there is no need to put negative here, okay. So this you can escape right now, okay. And say this is the case, and if you have a medal here, so first this Cl what it will do, it will actually form a bond with this, okay. And now the octet is complete. So how much electron is donated by this Cl negative, sorry, Cl? Only one electron when it is terminal, okay. But when it forms a bridge actually, if it is connecting say more than one metal, okay, say right, you have one metal here, so now it cannot share the electrons because it is having now its octet complete. So the only thing it can donate its electron pair. So when it donates the electron pair, that means mu2 means it is connecting the two metals. So how many electrons it is contributing? 1, 2 and 3. Okay, so that's why in the case of the mu2Cl, it will contribute in the form of the bridge, it will contribute 3. And for example, say if it is connecting more than two metals, say if it is connecting one more metal here, so again it will donate. So in that case 2, 2, 4 and 5. So in case of your mu3, it will donate 5. And in case of the mu4, say one metal is also there. So how many electrons? 7 electrons. Okay. So these things actually you need to understand. So however, this example just I gave you to actually so that you can have idea how we can count the electrons actually. So keep in mind this particular concept, and whenever I'll encounter with the different kinds of the ligands, I'll explain those things also. Okay. So see, if you want to know, if you want to determine the number of the metal bonds, okay, so it's quite easy actually. So first of all, you have to actually count the total number of the valence electrons. So in my last class actually, where I have explained the 18 electron rule and the 16 electron rule, I have explained how to count the electrons, contributions of the ligands, right, and electrons present on the metal, all these things. However, in my previous class, I have discussed only the case of the terminal ligands where no bridge ligand were there. But in now present case, I will discuss the bridge case also. So first you will determine the total valence electron, and say these total valence electron, you are saying that it is A. So it is just a formula actually which I have taken here. You may use any word actually. Okay. So in the step 2, once you get the total number of the valence electron, you please then you determine the value of the B. Okay, B it may see, you can see this B parameter again. It's actually it is some kinds of the electrons. So how this B you can determine? So N into 18 minus A. If your complex is following 18 electron rule, then it would be N into 18 minus A. But if it is following 16 electron rule, then it would be N into 16 minus A. Okay, and N is what? Number of the metals present in the your polynuclear organometallic compound. Number of the metals present in A, total number of the valence electron. This will give you the B. So once you get the B, and if you divide that B by 2 actually, then you will have the number of metal bonds, total number of the metal bonds. So half of the B will give you the total number of the metal bonds. Okay, and if you determine the if you want to determine the number of electrons present per metal, then what you will do, you will actually determine that total valence electron by the number of the metals present in the complex actually. This is as simple. Okay, this is quite simple. So all these things are quite logistic, and based on the logic actually these things are derived actually. Okay, so now you see, if the complex is following 18 electron rule and your electron counts like in that manner is 18, then there would be no metal ligand bond. But if it is less than 18 by 1 unit, that means the number of electrons are 17 only. That means one electron is deficient. Definitely there would be one bridge. Okay, that means not bridge actually. They definitely the connection between the two metals with the bonds, right? So one metal bond would be present if it is 17, right? By this formula. If by using that formula you are getting the total number of the electrons 16, then you will have the two metal bonds. For 15 you will have the 3, for 14 you will have the 4, right? And for 13 and so on, you can do just like that. Okay, so these things actually you have to keep in mind, and it would be quite easy if you do the practice. So for example, if you have given this particular complex and you have been asked, say for example, you have to tell the structure of that compound. So it's very difficult to actually remember or learn all kinds of the structure, but you have to do some kinds of the practice to in learning these structures. Okay, however some tricks are also there, some concepts are also there which are quite useful in deciding the structure of the molecule. So if you are first of all, if you want to determine the total number of metal bonds in it, so see in the first instance you can see here two irons are there, then there definitely these two ions would be connected by one bond. Okay, but it is not always the case actually, right? This may and this may happen, this may not happen. So first of all, in the step number 1, I will determine the total number of the valence electron, that is TVE, and this TVE, say I am calling it as A. So how I can determine? electron contribution by the iron. So you can recall the my last lecture where I have actually given you the list of the transition metals and told you that how many electrons actually each transition metal will contribute towards the bonding. So iron actually would contribute 8 electrons, and this iron is present twice, so 8 into 2. Okay, and this carbonyl is a neutral ligand, and it will always give you a pair of electron. That means 2 electrons would be provided by this carbonyl, as I have explained in my last class. So 2 into 9. So if you add 8 to the 16 and 9 to the 18, this will give you the 34. Okay, so this is the step number 1 which you have done. Now say in the step number 2, you have to determine the B. The value of the B, it is quite simple, n into 18, right, minus A, where n is the number of the metals. So how many metals are present? 2 metals are present. We multiply it with 18, right, minus A. Minus A is what? Total number of valence electron. So 18 to the 36, 36 minus 34, that will give you the 2. And if you want to determine the MM bond, right, in that case Fe bond, then this should be half of B. Half of B means, that means 2 by 2, that will give you the 1. So in that case, one iron bond is present. Okay, and so if you want to know the structure of that compound, so what you will do, you will straightforward write an iron here, okay, and another iron here, and you will connect this just like that. Now you have to actually put these 9 carbonyls. So 3 I am giving here, CO whole thrice, okay, and another 3 I am giving here, 3 3 6, and you left with the 3 another carbonyl. So first I am adding just like that, say this is in that manner, C double bond O. Second I am doing in that manner, C double bond O, and say third I am giving in that manner, C double bond O. Okay, so this is the structure. Now the important thing is that you will ask actually how we will decide that these bridging carbonyls are present or not. See guys, for this actually you have to remember structure, and there is one trick also. Whenever you have these two metals or any two metals which belongs to the 3D series, then you will always have the bridging ligands. Okay, how many bridging ligands would be there? It cannot be decided by actually observing this structure only. For this you have to have actually your complete structure. Okay, but whenever you have the first metals of the first transition series, then definitely you will have the metal bond in between them. Okay, so in that case you will see, if you want to write the structure properly for this one, then you will write this in that case, right, Fe2, and you see mu2 CO, and they are thrice. That means 3 carbonyls are connecting to iron. See, these are the 2 irons. One carbonyl is connecting here, another carbonyl is connecting here, and another carbonyl is connecting here. So this is the case, right? And rest you can write in that manner, CO whole 6. So this is how you can determine the structure. Okay, if you want to know the whether this is following the 18 electron rule or not, so it's quite easy. I have already used this particular formula. That means it is following the 18 electron rule. So if you want to know the total number of the electrons, per atom, total number of the electrons per atom, so you can write number of electrons per metal. Okay, so for this you will take your total number of valence electron and divide that number with the number of the metals. That means 17. Okay, so 17 electrons are present on one iron, and 18th actually will come through this metal bond. Okay, this is how you can determine the things. Okay, and then guys, you see, say I'm having my next compound, say this particular one. Okay, and you want to determine the structure of this one. So how I can go for this? So first of all, I will determine the total number of the valence electron, and I am writing this as TVE, right? And this TVE is actually A. So iridium, you know, it is the partner of, here see, cobalt, rhodium, iridium. So again, you can use my trick to remember that series, Komal Radha Ka Irada. So cobalt actually will contribute 9 electron. So when cobalt contributes 9 electron, then iridium would also contribute 9 electron. Okay. So 9 electron would be contributed by the iridium, and 4 times it is present, and carbonyl will always give you 2 electrons, right? 9 4 ja 36, and 12 into 24, 36 minus 24. Okay, so 36 minus 24, what it will give you, right? Sorry, not minus, actually add 34 26, it will give you the 60, I suppose. Okay, 60. So these are the total number of valence electron. If you determine the value of the B, that would be n into 18 minus A, where n is the number of the metals, 4. Okay, multiplied by 18 minus 60. Okay, so if you determine that factor, if you take the difference of these two, 18 fours are 72, and 72 minus 16, this will give you the 12. Okay, then if you determine the bond, right, present in it, so bond, half of B means, that means 12 by 2, that is 6. Okay, that means 6 metal bonds are present here. So how you can determine the 6 metal bond? So how many iridiums are there? You can write IR here, and again IR here, and again IR here, and again IR here. So total 6 bonds actually are there. So the bond number 1, bond number 2, bond number 3, bond number 4, bond number 5, and bond number 6. This is the only way by which you can connect these iridium ligands, iridium metals, with this 6 bonds. Okay, now again the question, you have your 12 carbonyls. So in that case, what you will do, you will straightforward write in that manner, CO whole thrice, and again CO whole thrice, and again CO whole thrice, and here again you can write the CO whole thrice, because this cluster, actually this complex network is not having a space to for this carbonyl to act as the bridging ligand. And I also told you, whenever you have, see, this is 3D series, and this is 4D series, and this is 5D series. So when you move down the group, so the tendency to form the bridge between the metal atom, right, it is decreases. Why it is decreases? See, see, whatever the ligands are there, say for example you are having your carbonyl, so it is having the p electrons. So when it is actually overlapping with the 3D, so there is very good overlap. When the overlap is very good, then definitely the bridge ligand would be there. But if you move down in case of the 4D, so there is poor overlap between 4D and the 2p, right? And then again there would be very bad overlap, even better, even more bad actually, overlap between the 5D and the 2p. So bridge cannot form. So this is the trick you have to remember. If you have the first transition series metal, then there is always a possibility of the bridge, while for 4D and the 5D you will not have any bridge. Okay, so in that case you will determine all these things. So if you determine the total number of the valence electrons, right, that means sorry, number of electrons per iridium metal. Okay, so this should be 60 total valence electron divided by 4. So 15 electrons actually are present on each iridium. Okay, so how they are actually coming through the ligands as well as its own electron. Okay, and then guys, you can see my next question. Say this is my question actually, and you have these complexes, complex 1 2 3. So intentionally I am taking this particular one, TCCO 10. So manganese, you know, manganese is contributing 7 electron. So this Manoj technical hairy, again my trick, Manoj technical hairy. So Manoj is manganese, and technical is TC, tectinium, and rhenium is Re, right? So 7 electron, that means all will contribute the 7 electron. Okay, so if you write, so there is error, it should be 2 actually. Okay, so if you determine the total valence electron, so total valence electrons, again this would be 7 contributed by this into 2 plus 2 into 10. Okay, 10 to the 20, 7 to the 14, 34 electrons. If you determine the B, so I'm not writing that formula again and again. So 2 into 18 minus 34, right? This will give you the 2. Okay, and then metal metal bond. Metal metal bond means half of B. That means 2 by 2, that is equals to 1. That means you are having one metal metal bond. So what you will write here, tactinium, and then again you have tactinium. You can write in that manner. Okay, and this tactinium actually belongs to the 4D series, so there is no chance of forming any bridge. So when there is no chance of forming any bridge, so what you will do, you will write CO 5 times here, CO 5 times here, as simple as that. Okay, so this actually you have to remember by solving the problems. Now coming back to the next problem, the problem number 4. Okay, CO2, whether we can check whether this is having any CO bond or not, right? This will decide. This is very important question actually, right? So again you see this cobalt actually would contribute 9 electron. So if you determine the TVE, total valence electron, okay, so that would be equals to 9 into 2. Carbonyls, see you guys, you must be thinking that why I am focusing on the carbonyl most, because these carbonyl complex are very very important. That's why I am taking these examples, right, commonly. However, I later on in the lecture I will take the another examples also. Okay, so 8 into 2, 9 to the 18, 8 to the 16, that will give you the 34. If you determine the value of the B, that will give you 2 into 18 minus 34. Okay, again this will give you the 2. If you determine the metal metal bond, that is half of B, that means 2 by 2, that is equals to 1. Okay, right, there, which simply indicates that what you are having say your cobalt and another cobalt, and remember it's a first transition series metal, right? So definitely the bridges must be there. So first of all you will connect that metal metal bond. Now you have to actually go for the bridges. So one bridge in that manner and one bridge in that manner you can write. And however, there is no actually trick or the concept to determine the number of the bridging ligands, right? So far I'm not discussing those things. Okay, so you have to remember certain things, and then you have 6 next carbonyls, so you will write in that manner. Okay, and if you want to determine the electrons per cobalt, okay, then your valence electron divided by the number of cobalt, that means 17. One cobalt is having the 17 electron, right? And see, this is guys something very very important, and this happens in the solid state. This happens in the solid state. Okay, but if you dissolve that compound in the solvent, in which in whatever the solvent it is soluble, say for example you are taking the N-hexane. If it is soluble in the normal hexane, so in the solvent actually these bridge actually will collapse, and when the bridge will collapse, then you will have this thing, CO4 and CO4. In that manner you can write. Okay, so in solvent in solution it is having no bridge, right, while in solid state it is having the bridge. Okay, and then I'm going for my next problem, right? Fe. So again this Fe contributes 8 electron. So these three actually, whatever you will calculate the number of the electrons for the metal metal bond, it would be true for all those, but the only difference would be in the structures, because this one will this Fe complex would have the metal metal bond, while rest two will not have the any metal metal bond. This I have explained. Okay, so how you can determine, again see I am going for this one. So total valence electron, that is TVE, which I am calling it as A. Okay, so that would be equals to 3 into 8, there is no problem. Okay, plus 2 into 12, 12 to the 24, and 8 to the 24, that is 48 it is giving you. And if you determine the value of the B, so it would be what your if you know the formula, then you can easily determine what was the formula. This was the formula, right? N number of the iron, 3 irons are there, 18 and 48, right? This will give you the 6, I suppose. Okay, if you solve that, this will give you the 6. So mm bonds, how many mm bonds would be there? Okay, that means half of B, that means 6 by 2. This is the value of the B, this will give the 3. That means 3 iron bonds are there. So how you can write? Fe, Fe. The only way you can connect this by forming a triangle in that manner. Since it belongs to the first transition series, then definitely the bridge would be there. Okay, so how you will form the bridge? So this cannot have bridge because it is already a bridge position. So you can write one bridge in that manner. Okay, and then you can write another bridge in that manner. Then you have now to 10 more actually carbonyls. Okay, so for 10 more carbonyls, what you will do is 12 2 are consumed here. Okay, and then you are having another. Okay, then how you will do? So you can write CO3 here and CO3 here, 336, and say 4 carbonyls are here. So you can write in that manner. Okay, so this is the structure. So number of electrons, right, per Fe atom, that would be valence electron divided by total Fe. Okay, and then it will give you the 16. That means one Fe is having the 16 electron. Okay, and if you correlate with this one, when it is having the 16 electron, okay, it will have the two metal bond. Okay, two iron bond. So how two iron bonds? You see this iron is forming one, this iron is also forming one. Okay, and if you see this one, this is forming one, this is forming one. Okay, so this you have to understand actually. So 2 means it is not like the total number of the metal, it is not actually total number of the metal bonds, it is the bond present between the two metal atoms, any two metal atoms. Okay, this you have to remember. Okay guys, so if you solve the problem for this ruthenium and the osmium complex, you will find the same result, but you won't have this bridge here. Okay, because due to the poor overlap, there would be no bonding. Okay, and then guys, my next example, which is, okay, again the same complex, say carbonyl complex, and see this question I have done already, right? This question I have actually solved. I have solved CO4. Yes, IR4 CO12. IR4 CO12. So CO4. The only difference would be whatever I have solved for this IR complex here actually, right? But CO actually will have the possibility of having your say bridge actually. Okay, so I'm not going to solve this particular problem. You can solve this problem by your own. Now I am moving to my next problem. Okay, and my next problem is this Fe4. Now I am having different ligand. Now I am having this ligand CP, cyclopentadienyl. Okay, cyclopentadienyl anion. This you have to remember. Okay, and if I take the neutral method, so this will provide 5 electrons. Okay, in neutral method this will give you the 5 electrons. I have already explained. So I am going to take first my total valence electrons. Okay, iron will give you 8 into 4. Okay, and my Cp will give 5 and it is present 4 times. Okay, and my carbonyl will give 2 and it is present 4 times. If you add all of them, 8 4s are 32. Okay, and 5 4s are 20 and 4 2s are 8. So this will give you the 60. Okay, then you have to determine that value of this one. So what was the value? Okay, formula n into 18 minus a was the formula. N is the number of the metals, 4 present. Okay, 4 into 18 minus this value of total valence electron, which is a, that is 60. Okay, so 18 4s are 72. Okay, and 72 minus 60, that will give you say 8, not 72 actually, 70, not 18, 4 8s are 32. Okay, and 32. So what is the difference? 4 8s are 32, 3 4 1 is 4 7, that's 60, 12. Okay, it should be 12 actually. Okay, so what it will give you? It will give you the 12. So your mm bond, half of 12, that is 12 by 2, that will give you the 6. Okay, let me check whether I have missed something. Okay, no problem in that. So you are getting this 6 metal bond. Okay, so how you can connect the 4 iron, right? This is Fe, this is Fe again, and you can write, say, sorry, I have to write here somewhere. Say this is Fe, this is Fe, this is Fe again, this is Fe again. Only 4 metals are there. So 1, 2, 3, 4, 5, 6. Okay, 6 bonds are there. Okay, so per atom, see, metal bonds per iron. Okay, so per iron you can see 1, 2, 3. Per iron they are 3 actually, right? So see, since this value is 12, you can see here. See, first of all, I have to determine the total number of the valence electron. Okay, sorry, electrons per Fe. So electrons per Fe would be 60 minus 4, 15 electrons. Okay, so when you are having the 15 electrons, okay, for 15 electrons, so 3 metal bond would be there. Okay, so 3 means, see, iron forming 1, 2 and 3, and this iron forming 1, 2 and 3. Similarly, this one is forming 3. Okay, there is no problem in that, but this is not having any space for actually your bridging ligand. So 4 cyclopentadienyl ions are there. So you can write Cp1 here, and see, you can put second Cp here, third Cp here, and then fourth Cp. Okay, and then you are having the carbonyls. Okay, then you can just like write the carbonyls here everywhere in that manner. Okay, and connect them all with the metal, only. Okay, not with the Cp. So in this way you can determine the structure. Okay, so this is quite simple actually. Now I am going for not so simple actually. I got confused in this calculation, but it was fine actually. Okay, so now I'm having my next problem, and in this problem you can see my tungsten is there, and this problem you can see it's a different kind of the different problem actually. Okay, so how I can solve this particular problem, you can see here. So there are two ways. So I am doing in the simpler manner. See, in the question itself, it is given that the mu, that means this mu Cl is there. So this is bridging chlorine, and this is your terminal chlorine. Okay. So bridging chlorine, how many bridging chlorines are there? 2 bridging chlorines are there, because it is twice actually. So it is up to you how you can write. So you can simplify that and you can directly solve. So if you simplify, then you will get W2 mu2 Cl twice, then your Cl twice, and then CO8, right? You can write in that manner. Now tungsten actually is the partner of your chromium group, karodpati moorkh woman, and it will give you the 6 electrons actually. So how many tungsten? 6 electrons, and 2 times they are present. And chlorine, when present as the bridge ligand, this I have told you here actually. When it is forming this mu2 Cl, then it will contribute 3 electron. Okay, this you should remember. So it will contribute 3 electrons, and it is present twice. And when it is terminal, then it will give you, it will provide only 1 electron. It is present 2 times. And carbonyl, doesn't matter whether it is terminal or non-terminal. Okay, it will always give the 2 electrons. So if you add all these things, okay, then how many electrons you are having? You are having 36 electron. Okay, 6 2 is 12, 3 2 is 6, 2 1 is 2. Okay, 36 electrons. Okay, and see, these are the total valence electrons, that A. Okay, so if you determine that this value, so you know n into 18 minus A, where n tungsten, how many tungsten? 2 tungstens are there, 18 times and 36. So 36 30 0, So 0. So 0 means no tungsten bond would be there. No tungsten bond. Okay. So how you can write the structure for this one then? So see, this is the tungsten W. Okay. And then you are having again C W, but there would be no bridge. Sorry, no linkage in between two. But you will have one chlorine here because it is given in the question. This chlorine is connecting two W, two tungstens, right? Then again you're having this chlorine and then two terminal chlorines. One you can give you to this one you can give you to this one, and then your 8 carbonyls, CO4 and then CO4. Okay guys, so in that case, very sorry, okay, this was the wire of my mic actually. Okay, so this is the structure. So if you want to determine the electrons per tungsten, so you can write 36 by 2, 18 electrons. So just following 18 electron rule, simply you can write in that manner actually. Okay, so you can see here, but again you can argue in that case this tungsten belongs to the 5D series. Okay, then how the bridging ligand is present present in that case? Because I already told you, see, whenever you have 3D 4D or the 5D metal, then the presence of the ligand would be crucial, right? Or would be difficult, but here you are having this one. Then again you can think one important point. See, chlorine actually will use your 3p electrons, 3p, say Cl17, right? If you write the electronic configuration, 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so the 3p and your say 5d, so their overlap actually not that poor, because size are not see, the size are comparable actually. If it was 2p, then there would be difficulty. Since it is actually belonging to the 3p, the chlorine are donating through 3p, so 3p with 5d can actually overlap. That's why you have this linkage here. So again a new concept is there. If you have the ligand which is donating to 3p or the 4p, 4p is not possible, say 3p, then there would be a chance for the for the bridging ligand in case of the 4d and the 5d series also. Okay, but not in case of the 3d series. Okay, so this is how you can understand. So this chlorine, see, if you want to determine, see this chlorine, how many electrons it is providing. So it is see, total it will provide 3 electrons, na? Okay, so 3 electrons out of 3, that it 1.5 it will give you to this, it will give this to this W, and 1.5 it will give to this W. Okay, so this is how you can distribute. Okay, or similarly you can do here also, but this is I think this is not necessary actually. So this is the structure you can draw. Okay, now say my next question. And my next question is, okay, I'm having my say eta 2. Eta 2 means hepaticity is given here. See, remember it is hepaticity is given. That means if this is your CH2, then the metal would be connected with this carbon as well as this carbon. This you should remember. This is not a bridge. Remember, this is not a bridge actually. Okay, this you have to remember. And this complex is given here. So I am solving this problem quite quickly actually. Okay, so how I can solve this problem? Say I'm having, say first of all I'll calculate the TVE, total valence electron. Okay, so for total valence electron, so this ethylene 2, 3, 4. First of all, see, we have to determine whether it is following the 18 electron rule or the 16 electron rule. So first of all, I will calculate the total number of the electrons. Okay, so ethylene, you know, see, ethylene is actually having 2 electrons. Okay, so 4 electrons. See, it is just like that. CH2, okay, it was just like that. So 4 electrons it is having, and 2 electrons it has already used to form the bond with the carbon, then it will having only the 2 electrons to donate actually. Okay, so one ethylene will give you the 2 electron. This I have already explained in my last lecture also. Okay guys, so you can see uh, 2 into 2. Okay, and then see, if you have difficulty, then you can understand in that manner. 1 2 3 4, this was the condition actually, right? Carbon having the 4 valence electron, and when 2 hydrogens are there actually in that manner, so one hydrogen here, one hydrogen here, so 2 electrons it is already actually used in the formation of the bond. Now it is having only 2 electrons, so it will contribute only 2 electron, and it is present twice, so it is 2 into 2. Okay, plus rhodium is the partner of the cobalt actually. Komal Radha ka irada, mitric. Okay, if it is giving 9 electron, then it will give you, it will also give the 9 electrons, so you can write 9, right? And hydrogen, you know, it is having 1 electron, only 1 electron, so it will always donate 1 electron whether bridged or not bridged. Okay, so you can write in that manner, say 1. Okay, and then 2 times, so 2 to the 4, 10, 14 to the 28. So total valence electrons are 28 actually, right? So that means it is not following your 18 electron rule, it is following your 16 electron rule. Okay, so if you did then you will use that formula to determine the B. B equals to n into 16. See in the question actually, right? If you have this type of question in your examination, then it will be given in the question, right? Whether it is square planar complex or whatever. See in the question which I was having actually, however I missed that point here, but it is the square planar complex. Okay, and square planar complex in my last lecture I already told you they follow actually the 16 electron rule. So you will use n minus 16 into A, where n rhodium, 2 rhodiums are present. Okay, 16 is there, A was 28, that means 4. Okay, 4 is there. So then you will have metal metal bond. Metal metal bond means half of B, that means 4 by 2, that means 2. That means 2 bonds would be present between the 2 rhodium atoms. Okay, then how you can write the structure? Say this is RH and this is RH, rhodium. Okay, and you see it is given that a hydrogen, 2 hydrogens are bridging. Okay, these 2 hydrogens are bridging, right? See guys, I have solved this problem directly, right? By writing the 2 outside. Okay, if you want, then you can go in this manner also. You can convert this into this one, and so that you cannot have so that you don't have the confusion in the bridging ligand. So the hydrogen is bridging actually, so your hydrogen is forming a bridge here, your hydrogen forming a bridge here, so 2 bridges are there. Okay, and you are having the 4 ethylene, so you can write in that manner, just like that. So when the bond is starting from the center, that means it is showing what, hepaticity of the 2. That means it is connected with the 2 carbons. Okay, in that manner you can write a structure, but there should be the 2 bonds between 2 rhodium, so you can write just in that manner. So it's a double bond, square planar structure. This is something very important. Okay guys, but if you change that hydrogen with the chlorine, then the scenario would be the different actually. Okay guys, so if you want to solve this problem, then you can write TVE, total valence electron, and that would be equal to, again, the same calculation you can do here, right? 2 into 2, okay, plus 9. Now this chlorine is the bridged one, and in the bridging position, when it is in the bridging position, I told you here, it will provide 3 electron. Where I have solved for this, somewhere I have solved actually, but okay, don't go too far. So remember this, when it is bridge, it will give you the 3 electrons, and they are present 2 times. So 2 to the 4, 7, 16 into 2, 32. 32 electrons are there. Okay, and if you want to determine the value of B, that means n into 18 minus A, that means 2 of the rhodiums are there into 18 minus 32, 18 to the 18 to the 36, that is 4. Sorry, 18 to the 36, 4. Okay, not like that, but this. Okay, 16, they are 16, very sorry. 9, 3, 12 for 16, 16 into 2, 32. Okay, 32 minus 32, that will give you the 0. That means no rhodium bond if the chlorine is here. Okay, so you can write rhodium here, you can write rhodium here, and you can form a bridge with the chlorine, you can form a bridge with the chlorine. Okay, then you have the same thing. Okay, no problem in that. So you can see here, only by changing the by changing one ligand, you have the different structure. Okay, so this is how you can solve the problem. Now your next, see this problem, you can see it's a heteronuclear type of compound, heterodinuclear compound. Okay, so why hetero? So this is iridium and this is rhenium. Okay, so you should know actually in which for which group actually they belong, to which group they belong. So I'm writing CORHIR, Komal Radha ka irada. So 9 electrons. Okay, and Manoj, technical hairy, that means rhenium, it will give the this will give you the 7 electron. So this rhenium will give you the 7 electron. Okay, and this IR will give you this iridium will give you the 9 electron, and then you will calculate your electrons. Okay, so if you use the neutral method, your CP actually cyclopentadienyl, it will give the 5 electron, carbonyl will give 2, iridium will give 9. See, carbonyl doesn't matter whether it is bridge or a non-bridge, so 2 into 2 because 2 times it is present, plus rhenium will give you the 7 electron, it is 2, and CP will give you the 5. Okay, this is how you can write. So if you add all of them, this will make 34. Okay, so when it is 34, then you can write you can determine the value of the B, and for the value of the B, you know, 18 into N minus A, that is 18 into 2 because 2 metals are there. Okay, minus 34. Okay, so that will give you the 2, and metal bond, you know, it is B by 2, so B by 2 means what? 2 by 2, that will give you the 1. So there should be one rhenium and iridium bond. So you can write Re here and Ir here. This is how you can write the structure. And CO, actually 2 CO are bridging ligand, so one CO you can write in that manner and another CO you can write in that manner. Okay, and then you left with your CP and CO, so you can write CO here and CP here, and then you can write your CP here and CO here. This is how you can write. So you can put both the CP in the one direction and both the CO in another direction, doesn't matter. Okay, so however this cannot be predicted whether it is actually the cis or the trans type of the compound, whether they are on the same phase or on the opposite phase, it is not possible since these two metals are different actually, na? So this molecule actually is unsymmetrical molecule. You should remember this point, this is unsymmetrical molecule. Okay guys, so these were the few problems actually which I have discussed in the determination of the metal bond. I hope you like the lecture. Okay, subscribe the tetrahedron chemistry classes if you understand the things. Do share with your friends. Okay, and press the bell icon for the latest notification, and don't forget to like the video. Okay guys, thank you very much.